We're going to continue investigating forecasting in this set of notes. Now we're going to focus on inference, meaning we want to say, like for example, we are 95% confident that the true future value at time point n plus 1 is between a lower limit and an upper limit, like what you would get with a confidence interval. Now, to do this inference, we're going to need to find a variance. Now, with most confidence intervals, of course, you have some kind of measure of variability in that interval. And what we're going to be interested in is a measure of the variance of the forecast, or more specifically, the forecast error. And using that variance, then we're going to take the square root of it, and we're going to find our interval. But to find this variance, we're going to actually need to rewrite our forecasts in terms of or rewrite our forecast using an infinite order moving average model. So similarly to what we've done in the past with our Arima model, we're going to rewrite it now as an infinite order moving average model. So to help see how this process goes, let's go back to our autoregressive 1 example with mu equals 0. And as we've seen, we could rewrite that model where we just have x of t on the left side, and on the right side of the model, we have brought over that AR component, and we can rewrite this as an infinite order moving average model. Let's see what happens then to our forecast. So x tilde with a subscript n plus m, and a superscript n means that we want to go m time points into the future to forecast what that x value will be using information that we have available to us up until time point n. And this just simply represents what's the expected value of x of n plus m given my past. Okay, so let's write our model then in terms of that infinite order now moving average, where I just replace t with n plus m. And we can then, the stuff that's in parentheses, we can move it through, we can multiply it by the w's, and so we get the expected value of w sub n plus m plus phi 1 times w sub n plus m minus 1, and so on, all that given my past information. Now, if m is equal to 1, so I'm going 1 time point into my future, let's look at what happens. So everywhere I have an m, I'm going to replace it with a 1. So I have the expected value of w sub n plus 1 plus phi 1 times w sub n plus phi 1 squared times w sub n minus 1 plus dot dot dot, given my past information. I can move that expectation inside the sum, factor out the constants, and look what I get. Well, I have a 0 here because I have the expected value of wn plus 1 given I sub n. These w's are independent with mean 0, variance sigma squared. I have information up to time point n, so n plus 1 has not been observed, and as we've seen before, this expectation then is simply 0. But now the expected value of phi 1 times wn is phi 1 times wn, because again we have information up to time point n and we have essentially observed what wn will be. So that's why I have that there, and we can keep on going writing everything out. Okay, now you might be thinking, okay, wait a second, this forecast doesn't look the same as what we've had previously. Previously we had a forecast that was phi 1 times x of n when we had 1 time point in the future. But these are actually the same. So let's write out what xn plus 1 tilde n, or x tilde, so n plus 1 with a superscript n. Let's write it out in terms of the w's. How about we replace each of these w's with the corresponding x version of it? So again, wt is equal to xt minus phi 1 times xt minus 1. So I replace wn, I replace w sub n minus 1, and I keep on going. Look what's going to happen then here. Notice I have an xn minus 1 here times a phi 1 squared. I have phi 1 times xn minus 1 here, but I also have a phi 1 out in front, so I have phi 1 squared times xn minus 1. So what's going to happen is this. This part is going to cancel out with that part. Or if I were to actually multiply everything out, have that cancel out like that, and you're going to have a whole bunch of stuff that's all going to cancel out. And so you're left with just simply phi 1 times xn, which is exactly what we had before. Okay, well, what if we have m equal 2 then? So here's my model, or here's x of n plus 2. I want to find the expected value of that given my past information. I write out my model in terms of all now the w's. And again, whenever we have a subscript that's greater than n, that corresponding expected value for that w then will be 0. So look what I'm left with now. Phi 1 squared times wn plus phi 1 cubed times wn minus 1 plus and so on. Here's what it looks like when we go 3 time points into the future. The same thing happens. Okay, so this illustrates how these forecasts are the same if we rewrite our model in terms of an infinite order moving average. This is going to be useful then very, very shortly. First of all, I want to talk about forecast error. So again, our goal is to get at what x to the n plus m is. This is the true future value. We don't know what it is, but our goal is to estimate that as best as we possibly can. And we estimate it then with this x tilde version of it. So we have the observed value minus the forecast. And so if we somehow could actually get this future value, we would have a way to see how far are we off. In other words, the forecast error. We need the variance of that forecast error to derive a confidence interval for this true future value. So we are going to be very, very interested in finding the variance of x of n plus m minus the corresponding forecast. Now, do note, some books will, I don't know why they do this, sometimes they'll use different notation for this particular variance. So for example, Sumway and Sulfur's book uses this symbol to represent the variance. I'm not for sure why they need to do that. Okay. So with that then, we can come up with an approximate 1 minus alpha times 100% confidence interval for x of n plus m. So, as you see in many different confidence intervals, you take the estimate plus or minus the value from the standard normal distribution. So we have the 1 minus alpha divided by 2 quantile from the standard normal. If alpha was 0.05, this value then would be plus or minus 1.96. And then we take the square root of now the estimated variance of that forecast error. So this square root of the estimated variance, another name for that, of course, is standard error. Well, where did this equation come from? Just to make sure you see this, so I could have 1 minus alpha is equal to the probability that I have a statistic that is between two values for my standard normal, these two quantiles. What is the statistic? Well, approximately, oops, let me erase that, excuse me, xn plus m minus the forecast just a second while I write everything out here. So one can say that approximately the statistic that's in this middle here, the standardized value essentially, has a probability of 1 minus alpha of being within these two standard normal quantiles. And let me just emphasize that this is approximate. So now that I have this, then I can do a little bit of algebra. I can let me actually bring out a different color pen here. There we go. Maybe not. That's a weird looking pen. Let's do this one. I can bring my I can take this square root of this estimated variance. I can put it on both sides of my equation just by multiplying through. Then also I can add and subtract. I'm sorry, I can add to both sides this statistic here. I don't know why my pen's disappearing, and put it also on the other side. And then this is how I derive my confidence interval. If you need more details on that, let me know. But this is the standard process that, again, you would learn in a mathematical statistics course. But I'd be happy to give more details if needed. Okay, so this is, let me do a little bit of racing here. This is a confidence interval for the true value in our future. I call this a confidence interval. Others may want to call this a prediction interval. So for example, in a regular old regression setting, you learn about a confidence interval for the expected value of y, where y is the response or the dependent variable. You also learned about a prediction interval for just y. And this is called, we have a confidence interval here, we have a prediction interval here. This different terminology is used to help introductory statistics students understand the difference between the two intervals. One is for a constant and one is for a random variable. Here we are finding an interval for a random variable. So because of that, sometimes you'll see time series textbooks call this a prediction interval. In the end, when we're doing frequentist-based inference, all these things are simply just confidence intervals. The name prediction interval is just meant for introductory students to help them differentiate between the two. Everything is still just a confidence interval. And so because of that, I'm just going to call this a confidence interval. Okay, so let's look at what that confidence interval would be for autoregressive 1 model with mu equals 0. So when m is equal to 1, let's look at what the forecast error would be if I rewrote everything in terms of that infinite order moving average model. So x of n plus 1 itself would be wn plus 1 plus phi1 times wn plus phi1 squared times wn minus 1 plus, and so on. Then oops, I'm drawing it to the wrong place, excuse me. Let me emphasize this. In fact, I can use a highlighter. Okay. Now, this forecasted value then, what we had just derived previously, has a value of phi1 times wn plus phi1 squared times wn minus 1 plus, and so on. Okay, so we'll draw an arrow there. So look what happens here. We have things cancel out because we have that negative sign there. And what we're left with only is wn plus 1. So that's our forecast error. We're going to come back to that very shortly. For m equal 2, my true value in the future, written in terms of my autoregressive, the infinite order moving average version of that autoregressive 1 model, is what's highlighted there. Then the predicted value, the forecasted value that we had just derived in the previous example is shown here. And look what happens. This cancels out with that. This is going to cancel out with that next term there. And what are you left with? wn plus 2 plus phi1 times wn plus 1. On your own, you can go through the details for m equal 3. And look what we're left with here. We have one more term right there. And also take a look at this. I had phi1 raised to the 1 power. You can say I have phi1 raised to the 0 power there. I have phi1 now raised to the 2nd power for that third term there. So we are starting to see a pattern. Okay, so let's take now, remember what I need. I need the variance of this forecast error. So I need the variance, this is for m equal 1. I need the variance of W sub n plus 1. Well, we know what that is. Because it's white noise, that variance is sigma squared W. For m equal 2, I need the variance of that forecast error. Well, let's take that forecast error, put it inside our variance formula. Now remember, the W's are independent of one another. So because of that, I can move that variance through the sum without worrying about any covariances. Also, any constants that are there in terms of multiplied by a random variable, those come out as squared terms. So this leaves me with the variance of Wn plus 2 plus the variance of phi 1 times Wn plus 1, which is phi 1 squared times sigma squared W. For m equal 3, we have the same thing occur as well. Notice again, we see this pattern here. We have let's say a phi 1 raised to the 0 power, a phi 1 raised to the 2 power, a phi 1 raised to the 4th power. And we always have a sigma squared attached to all of them. So because of that pattern, we can come up with a nice compact form for what the variance will be for that forecast error. It's always going to be sigma squared W times the sum from I equal 1 to m of phi 1 squared raised to the I minus 1 power. Now when you look at that initially, you might be thinking, wait a second, I'm not quite sure that this is truly what I get from looking at this. And so this is where you can do a simple example. Suppose m is equal to 1. I have sigma squared W times the sum I equal 1 to 1 of phi I squared, that quantity to the I minus 1 power. Notice my sum is very boring. It's only I equal 1 to 1. So when I put a 1 in there, 1 minus 1 is 0. And this then becomes a 1. And so the sum becomes a 1. And I just multiply it by sigma squared W. On your own, verify for m equal 2 and m equal 3 that indeed this all works out. So now that I have this variance then, let me do a little bit of erasing. Now that I have this variance, I'm going to need to find an estimate of that variance. How do I do that? Well, I'm just going to put a hat on top of there. I'm going to put a hat on top of there and a hat on top of there. So I just replace it with this corresponding estimated value. So then the approximate 1 minus alpha times 100% confidence interval for the true future value, m time points into the future, is as follows. It's that forecasted value plus or minus the value from the standard normal times the square root of that estimated variance of that forecast error, which is what is shown there. There's my confidence interval for x of n plus m. Now let's take a closer look at this interval here. Look what happens as m increases. So as m is increasing, remember phi hat 1 is a number between -1 and 1. As m is increasing, this sum is going to increase as well. The amount that's going to increase for each m is going to become smaller and smaller and smaller because phi 1 is between -1 and 1, and I'm taking the square of it. So if this sum is going to get bigger for each m, that means then the number that I multiply that standard normal quantile by is going to get bigger as well. And so the effect then on the confidence interval is going to become wider and wider and wider, where the amount that's going to become wider is going to be less and less for each m. And so think about why this makes intuitive sense for a confidence interval to get wider as m is increasing. The intuitive aspect is that as I get farther and farther and farther away from my data, I am less certain, let's say, about what my future value is going to be because I'm getting farther away from where my data was actually observed. And in order to still remain at the certain level of confidence, like 95%, I'm going to need my interval to get wider and wider and wider as m is increasing. We represent uncertainty in statistics by the variance. and we can see that we become less certain as m increases. Okay, so that's for AR1. Well, what about an Arima Pdq model? Well, guess what? We're going to have to rewrite everything still as an infinite order moving average. And we saw that that process, the derivations behind it, can be kind of time consuming to actually do. So let's just go through a little bit of the details here. Okay, so here's our Arima Pdq model. What I can do is rewrite it so that I have my MA operator divided by the AR operator and the differencing term. I can set all that equal to psi of b, which is this infinite order linear combination of the psi's and the b's. So what that means then for us is that if I were to take a look at my forecast error there, then I can rewrite this forecast error always as a sum from I equals 0 to m minus 1 of psi sub I times w sub n plus m minus I, where I'm just going to, for notational convenience, I'm going to take psi sub 0 is equal to 1, so I can always keep a psi in that. Okay. Investigate this on your own, that truly this does work out. So for example, with an AR1, if m is equal to 1, we can see a very simple case of this. So if I have m equal 1 up there, I'm just taking the sum from I equals 0 to 0 now. And what am I left with? Well, psi of 0 times w n plus 1 minus 0. In other words, psi 0, wn plus 1. I'm sorry. In other words, just w sub n plus 1. So this matches what we had previously for the AR model. So what is the variance now of this forecast error? Well, I can just simply stick a var here and a var on this side here. The w's, remember, are going to be independent of one another. The psi's are constants that can be factored out of the variance and squared. And this is what I get. Here's my variance. Sigma squared w times the sum I equals 0 to n minus 1 of psi I squared. So then this leads to then the actual 1 minus alpha times 100% confidence interval as follows. My forecasted value plus or minus the value from the standard normal, sigma hat sub w times the square root of that sum that we had just seen. Okay, so let's take a look at an easy example. This corresponds to moving average 1. Our moving average 1 essentially is already written as then this infinite order moving average model where theta 2, theta 3, and so on are all equal to 0. We can then translate this in terms of the psi. So psi 1 would be theta 1, psi 2 would be 0, psi 3 would be 0, and so on. So that my variance that I would need for the corresponding interval, let me just mention something really quick just to make sure this is clear. Notice for the interval that I actually calculate here, of course I'm going to need an estimated variance. For some reason that's disappearing. I'm going to need that estimated variance, so that's why you see hat on top of the psi. So the psi's are written in terms of phis and thetas. Just put phi hat and theta hat in there when you're working with a psi hat. Okay. So here's my true variance, sigma squared w times the sum. When m is equal to 1, again, I'm just going to have with the sum a psi 0 squared. Psi 0 is always going to be 1. So now I'm left with sigma squared w. Now for m equal 2, look what's going to happen. I have sigma squared w times the sum of psi 0 squared plus psi 1 squared. Notice when m is equal to 2, I'm just going to have two terms that I'm adding over. The psi 0 is 1, psi 1 is theta 1. And so this is how I get then my corresponding variance. When m is equal to 3, I'm going to get exactly the same thing because those corresponding size that would be included, these new size that would be included in that sum are all equal to 0. So let's take a look at another example. This deals with an Arima 111. So here's my corresponding model. I'm going to rewrite it as an infinite order moving average. So because of that, then I'm going to need to figure out then what the corresponding size would be in terms of the phis and the thetas. Okay, we've went through this process in the past. So because of that, I'm not going to go through every single detail here. But basically, just to summarize, I'm going to multiply out this 1 minus phi1b times 1 minus b. I have that there. And then what I'm going to do is take this term that I've underlined here, multiply it by each of the corresponding terms here. And so that's what I do here. And I'm still setting this all equal to 1 plus theta 1 times b. Then I match like powers of b throughout when I equate like powers of b on the left side and the right side so I can figure out what the phis end up being. I'm sorry, the size. So psi 1 is going to be 1 plus phi 1 times theta 1. Psi 2 is going to be, look at this, psi 1 times 1 minus phi 1 minus phi 1. Look at psi 3 as well. Notice how psi 2 is in there, psi 1 is in there as well. So we start seeing a certain pattern that arises. Then with that, I can go ahead and find my variances. So for one time point into the future, again, sigma squared w is going to end up being what it is. For 2 time periods in the future, I'm going to have 2 terms relative to the size. So here is psi 0 squared. Here is psi 1 squared, based upon what we had up there. Okay, so now let's look at doing some of these computations in R. We're going to work with this AR1 example first. Now previously we found sigma hat squared to be about 1.34, phi hat 1 to be 0.69. The square root of the estimated variance of that forecast error, in other words, the standard error of the forecast error, is automatically found by the predict function when I specify se.fit is equal to true. And so as we've seen previously, here is my first forecasted value. Now, in the SE part of the return lists from using the predict function, I get in a TS class format, I get these corresponding standard errors. So this 1.155698, if I guess Word's not going to let me write. Let's see what happens if I keep on writing it out faster than it can delete everything. And we're going to take the square root. So this variance right there, or the square root of that variance, is 1.16. Okay. So let's go ahead and now find these confidence intervals. Here's the actual expression that we found for these confidence intervals before. We can more simply find these confidence intervals by using the information that's stored inside my for.mod object that results from predict. So I take my forecasted value from pret. This is going to be a vector of length 5. Then I subtract off the value from my standard normal distribution. If I'm finding 95% confidence intervals, this value is going to be negative 1.96 here. And then I take my standard errors, which is also going to be a vector of length 5. R is going to match everything up. It's going to take the first element of the vector of pred and match it up with the first element of the vector in SE, so that when it does this math, it can actually calculate 5 intervals essentially all at once. I'm going to put that in my lower bound, or my low object, which is my lower bound. And then for my upper bound, I'm going to create an object called up. And the only difference with that code is I'm going to put a plus there instead. I'm going to put this information, I'm going to display this information to a nice little data frame, and this is what we get. So the 95% confidence interval for x of 101, 100 time point 101, is the upper bound is 3.53, the lower bound is negative 1.00. There's the first confidence interval. My last confidence interval, look how it's getting wider now, negative 3.13 to positive 3.01. Again, it's getting wider as a way to represent the uncertainty of getting away from the data that was actually observed. So in this next table here, I show you how to do some of these by hand calculations. On a test, you may need to actually do these by hand calculations to verify that indeed what R gives is correct. So previously we found this forecasted value for the first, for m equal 1 to be 1.26. Here's then the corresponding estimated variance for the forecast there. It's just simply sigma hat squared w, or 1.336. If I put this all together into my confidence interval, I get exactly what we did up there. On your own, take a look at time point 2 into the future, time point 3 into the future as well. In these cases, I actually did all the math where I had the sigma hat squares there, I had the phi hat squares there, to show that indeed you will get the same answer as what's shown by R in the output. Okay, so now let's go back to doing some of these plots that we've seen previously, where we have the time series itself, we have the corresponding predicted values from t equal 1 to 100. Then we also have the forecasted values from time 101 to 105. Now we can also plot the corresponding confidence intervals too. So this code right here is not new. The third line here is what's new. This is what's going to give me my lower bound in my plot. So I use the lines function again. I'm going to use, remember I saved the lower bound in low, so that's going to be my y argument. The corresponding x argument is what time points these are at, 101 to 105. Again, this is going to give me by integers. Line width is just 1, the default. The color is dark green, and I'm going to use a line type of dashed. For my upper limit, I'm going to do exactly the same thing, but use lines with up as the y argument. I'm also going to put a nice legend on the plot too. Note that I don't have any plotting points corresponding to the actual confidence intervals for a particular time point. You could put them on there if you really wanted to. I typically do not see people do that, so that's why I left it off. And since I don't have an actual plotting point, I'm only doing the line itself. For the plotting character in my legend function call, I put an NA for not available. And this is what we get here. So we can see, here's the upper bound of the interval, here's the lower bound. Now also what I can do is zoom in. So I'm going to zoom in from time point 96 to 105 so I can see this better. And this is what we get here. So again, that first confidence interval is at time point, time point 101, right there. Let's get the actual numerical values real fast. So negative 1 to 3.5. So this is at negative 1, and this is at a positive 3.5, as we can see there. And so there is the bound. Since I'm using the forecasted value plus or minus, then the same value, the quantile from the standard normal times that standard error, that's why the forecasted value, of course, is right in the middle of those two plotted intervals. And so we can see again here how these intervals are becoming a little bit wider as the time is increasing there. Okay, so now, well, let me actually go back here. So, what could this be used now? Maybe let's say this AR1 model was used for sales for a company, where each of these time points might be months, maybe quarters, or it could be years. So if a company wanted to, let's say, forecast what their sales would be for next year, they could use this kind of a model, use the corresponding confidence interval associated with it as well to give some kind of measure of the uncertainty of what that true future value would be. So this is what this kind of a model, what the forecast and the confidence intervals would be used for. That's one example in terms of sales for a company, but you can think of many other financial applications as well. Later in the semester, we'll also take a look at examples dealing with enrollment at a university. It could be used for measuring the number of sunspots. There are a wide variety of uses for this kind of information. Because so often in real life applications, we want to know what's going to happen next. And that's what time series analysis gives us. It gives us some confidence then, like with the confidence interval, of what that future value will actually be. So let's now take a look at an Arima 111. Remember, we have 200 data points. Here's just some of the same output that we've seen before, where I estimate my model. I get my forecasts out using the predict function. Notice how I have se.fit equal true there. I put the results into an object called for.mod for forecast from the model. And for.mod is a list. I have a pred component. I have an se component. So this 3.09 there is the square root of the estimated variance of x sub 201 minus x sub 201 tilde superscript 200. I can then use the same code as I did before to get the corresponding confidence intervals as well. And so for the first forecasted value, so at time point 201, fortunately Word is sometimes removing my writing that I have on the screen. The bottom bound is negative 492.42. The upper bound is negative 480.30. That's my first 95% confidence interval. Sorry if I didn't mention that it was a 95% confidence interval. Next, I show how to go through the by hand calculations here. Please verify that you can actually do this. So at time point 1 into the future, of course, this variance is kind of boring, you could say. It's just sigma hat squared W always, 9.558. If you go through the math, I get exactly the same interval as I do up there. Here's time point 2 into the future. Again, this is going to become more complicated, especially since now I have a Arima 111 model. But I do show how one could just simply plug in the corresponding parameter estimates, get the corresponding variance of 53.334, and just for emphasis. If I were to take the square of 7.3, I get that 53.334. Now I can then go ahead and find my corresponding confidence interval, negative 499.25 to negative 470.62, which is what's shown in the output. Okay. Now, time series analysis is often presented in a course it's often taught using simulated data because it helps students understand what I would expect to happen actually does occur once we include all the math, once we include all the statistical calculations in it. Now, one additional reason why time series analysis is often presented in a teaching aspect from simulated data point of view is because since I'm simulating the data, I could simulate a few more observations and actually observe what the true future values would be for a time series. And in fact, that's what I did with this Arima 111 example. So when I actually simulated the data, I didn't simulate just 200 observations, which I have been showing you before. I actually simulated 210 observations. And so because of that, now I can compare these. I can compare x of 201, x of 202 down to x of 210. I can compare those to what my forecasts are, to what my corresponding confidence intervals are as well. Okay, so I have this table here that does this comparison for us. I have M as the first column. The second column is my corresponding forecast. I'm going to go 10 time points into the future. I have all the corresponding 95% confidence interval lower and upper limits. And then these, I don't know why I have a capital X. It shouldn't be a capital X. These are my true future values. So the actual X201 is negative 494.85. The forecasted value for that, using the first 200 values, is negative 486.36. So I'm off by about 8. Take a look at the 95% confidence interval. Negative 492 to negative 480. Uh-oh. The true value happens to be outside the confidence interval limit. And in fact, this happens for the first 6 future time points. It stops once you get to time point 7. So let's actually take a look at this on the plot. And so here's my usual plot. The red is what was originally observed up to time point 200. The black is the predicted value up to time point 200, and then also the corresponding forecasted value past 200. The dashed lines are the 95% confidence interval. Notice how they're getting wider as M is increasing as we get farther away from my data. And then in blue here is what's new. You can take a look at the code in my program. The blue is the true future values. And we can see that the interval is not capturing the first 6 of these true future values. It's close, and we can see that. But the 95% interval is not capturing it. So I was kind of surprised to see this, but again, you have to remember, though, we are only 95% confident. So there's bound to be some cases where the interval doesn't capture this true value, and this, in fact, is one of these particular cases. But because of my concern, I decided to examine a few other realizations of this time series to see if what I'm seeing here is a rare event. And in fact, as you would expect for doing inference with a high level of confidence, this was a rare event for something like this to happen. In my other situations, the confidence intervals did contain the 10 extra observations. Okay. So that concludes in this example. But there's one last thing I want to do to talk about before I conclude this entire section. And that is, all forecasts and associated inferences assume that what has occurred in the past will occur in the future. Thus, trends seen in the past will continue in the future. Well, what happens, though, if this does not occur? Well, then these inferences, all the work that we've done here, you can somewhat, almost you could say, throw it away. Because this model, and in fact any kind of statistical model, it doesn't have to be time series analysis, any kind of statistical model is assuming the trends, the relationships that you have between variables, those relationships, those trends that occurred when the data was observed are going to continue again later on if you were to take another sample, or you could say into the future. And so As long as these trends, these relationships hold true, our models will predict correctly in terms of what we expect in terms of our inferences that we have with like 95% confidence. Otherwise, though, if things change, for example, suppose we are modeling, now in the time series analysis, we are actually modeling the sales of a particular company. And you might, let's say, forecast for 1 year into the future, 2 years into the future, 3 years into the future. If, let's say, the company sold part of itself to another company, well, of course, sales are likely to go down. So those forecasts, that model does not hold anymore. And that seems intuitive that that would happen. But let's say, we have some kind of company that's selling a product to consumers. And perhaps some kind of new technology and innovation comes about where that company's product is no longer as desirable as it once was. Well, let's say that happens at year 2 into the future. Well, the forecasts that you've been making from that model cannot now be used now into the future because we have this assumption. What has happened in the past will continue into the future. And something like a new technology innovation, though, can totally screw things up. Your model is not going to be worthwhile. So what you're going to need to do is come up with new forecasts, a new model that somehow takes into account that technology innovation. Okay, so that's just some big picture stuff to always consider when you're doing anything at all with statistics, not just time series analysis. So then that concludes in this section on forecasting.